So far in this series, we've learned to use a marine sextant. We've shot objects in the sky. We've found them using the geographic position, the declination, the GHA. We've used the nautical almanac to construct a triangle. We've used HO 229 to solve that triangle. And in this final step of the process, we're going to compare what we computed with HO 229 or other methods to what we observed in step one so that we can plot that line of position onto an actual chart. Hello, iguana. I don't have anything for you, I'm sorry. In this film, I'd like to talk about the last step in the process. So far, we've used the sextant to shoot and correct a sextant measurement. We've used the nautical almanac to determine the geographic position of the sun. We've built a triangle using some hard thought and then used HO 229 to solve that triangle to give us a computed value. The essence of this step is somewhere out there, there's the geographic position of the sun, the spot directly beneath it or whatever celestial object we're using. We've used the sextant to measure the angle or a proxy for the distance from it, the zenith distance. In this step, what we're going to do is we're going to calculate an azimuth, which is a direction to the object, and an intercept. Are we closer or further from where we thought we were from that object? So just like a radar fix with a bearing and a range, we're going to end up with an azimuth and an offset or an intercept to help us draw that line of position. Let's dive into it a little bit more. In step one of our 5-step process, we determined the height observed. This was the height of the sextant corrected for index error, dip, refraction, etc. In step 4 of the process, we determined our height computed. This was the result of creating and solving a triangle to determine the height that the celestial body would be at if you were standing at the assumed position. It's now time to compare these two. So we're at the point where we compare these values and can determine a difference by simple subtraction. For instance, if the HO was 49 degrees and 12.7 minutes above the horizon, and our height computed was 49 degrees and 04.9 minutes, this height computed is calculated as if you were standing on the assumed position. You're not. There's a difference. In this case, it's 7.8 minutes is difference. So this may seem simple and mundane to determine the difference between them, but it's a very, very important part of the whole process. So let's buckle in and talk a little bit about theory. What's actually happening in this case? Well, let's imagine that the sun is up here in space, and this is the GP right beneath it. And then you're out here on your ship. You use your sextant to measure an angle between the horizon and the celestial body that's up in space. If you were in this position, let's call it position alpha, if you could modify this a little bit, right? If you moved to position Bravo and now your ship was here, you're going to measure a different angle. It's going to be bigger. And as you get closer and closer to the GP, to position Charlie here, the angle continues to get bigger and bigger. So as you get closer to the GP, the angle that the sun or celestial body appears at is going to increase. Just get bigger and bigger as you move on there. Likewise, if the sun was out there on the horizon down to the GP and your boat was here, if you went further and further away, the sun would get lower and lower on the horizon for a given moment of time. So in essence, what we're trying to do is compare this height observed and this height computed to figure out, are we closer or further away than the height computed? So for instance, in this case, the height computed was 49 degrees 04.9. So that was the angle that they saw the sun at above the horizon. Is the height observed more or less? Well, it's more. So in this case, we're closer to the GP than the height computed. So the height observed over here is 4912.7. It's greater. So a simple way to quantify this, or to remember how to work this, is do the subtraction between the two and then determine which one is greater. So if the HO is more, then you are towards the GP. So HO is more, you're towards the GP. And likewise, if the computed was greater, then you're away from the GP. So depending on how this math works out, you're either going to be towards or away from the GP based on the height computed. If we were to plot that, on a top-down chart, if this was like a nautical chart here or a piece of paper that we use to simulate a chart, we're eventually going to plot the assumed position. And then we're going to plot the azimuth, the Z value and the ZN value to the GP. What we need to know is when we get to this plot, this assumed position, this intercept here, are we towards the GP or are we away from the GP? So when the time comes to plot this in a couple of lessons, this is going to be important. So the key takeaway for this lesson itself is to take the height observed and the height computed, calculate the difference between them. Usually it's just simple subtraction. Then remember, if the HO is more, you're towards, and if the computed is greater, you're away. These two memory aids will serve you well working forward from there. So for now, let's practice just this skill, and then we'll move on to tie it all together in the next series of videos. Earlier in step 4 of the process, we talked a little bit about this leftover declination, the declination increment, especially when we were dealing with height computed. We used the D value, the altitude correction factor, to kind of correct this height computed for the remaining declination increment in certain situations. We also said at the time that the Z to ZN issue was not sufficiently important to correct for in this case, right? It's never going to be really more than a degree, and for practical celestial navigation purposes, we don't need to account for the declination increment when dealing with the azimuth angle. However, if you want to, this video is going to talk a little bit about how to do that. So if we had a latitude of 25 degrees north, a declination of 23 north, 23.1 minutes, and an LHA of 100, you would pull out a Z base value of 78.7 degrees. So normally this is going to be perfectly fine for celestial navigation math. We would use this and turn it into a ZN depending on what our specific circumstance was. However, if you do want to account for this 23.1 leftover declination increment, we can talk about how to do that. The reason I bring it up is because sometimes you only want to use the azimuth. So if you're on a sufficiently large ship that has a gyroscopic compass, you may want to check for the compass error. And you can do that by determining the exact azimuth to a star or other celestial body, measuring it, and comparing the calculation to the measurement, which is kind of a theme of celestial navigation, measuring something and comparing it to a calculation. So if you did want to do that, or if you just simply want more accurate azimuth data when you're doing celestial navigation work, we're going to talk about that in this video. So given these, the first step is going to kind of look at the base values. So our latitude was 25 north, our declination 23, our LHA 300, we ended up with this base value of Z of 78.7. If we want to account for this increment, we need to kind of note that increment and take a look at our correction factors from there. What we'll do is we'll look in HO 229 at the next subsequent value for declination. So instead of 23, we'll look up 24 degrees, and we'll see what base value pops out there. In this case, it's 77.5 degrees. So you can see between declination 23 and declination 24 degrees, this Z value changes by not that much. It's about a degree or a little bit more. However, it's enough that it's significant. So what is the difference? The difference is 1.2 degrees, and it's a negative difference because it's getting smaller and smaller. So the increment here was 23.1. So if we multiply this by the increment, 23.1 minutes, and then divide the whole thing by 60, you'll end up with a correction. So that correction ends up being negative 0.46 degrees, or roughly 0.5 degrees. So now you can take this base Z of 78.7, subtract the 0.5, and get a new base Z of 78.2, which you can turn into a ZN depending on your circumstances of where you're at in the world. So this is a tedious process. for very little gain. You're only changing this by half a degree, and when we go to plot all this stuff, you're not going to get much bang for the buck there. However, it is important when you're doing gyro compass error, or if you want maximum accuracy. In essence, we're accounting for this declination increment with this process here. Often we can't plot on a real chart when we're doing celestial navigation, so we've got the universal plotting sheet to help us do that. These sheets are available on the internet. You can purchase them, and a whole stack of them is relatively inexpensive. What it does is it allows us to create our own chart based on roughly where we are. These are preset latitude lines. Since latitude lines are parallel all the way from the equator to the pole, latitude is also known as parallels. We can use these, and then we just simply have to adjust this for our longitude based on where we're at in terms of latitude. So if we were to pick, say, a center latitude of 25 degrees north, then we can coordinate the rest of these latitude lines to be 26 north and 24 north. Now, longitude is not parallel like latitude is. Instead, longitude changes from the equator to the pole. So at the equator, longitude lines are maximum, and at the pole, they're very small. This outer ring here allows you to calibrate this for your latitude. You can also do that down here on the longitude mid-latitude scale. So, two ways to do it. First, you can take your rolling ruler or triangle or whatever you like to use, make sure that it's set up and calibrated properly, and then choose 25 here for the center latitude. So this is 10, 20, 25. Make sure it's also 10, 20, 25 down here, and you can draw a longitude line that way. And you can choose what you want these longitude lines to represent. So let's say it's 144 degrees west. This would be 145 degrees west. From there, you can choose to use a divider to set your longitude markers, and then you can put one over on this side. You can extend it out this way if you wanted as well, or you can kind of count up the 10, 25 marks, so 10, 25 marks, and do the same thing over on the left side of the maneuvering board. So that would be another way to do it. Alternatively, at the bottom right of the scale, it says longitude and mid-latitudes, and these numbers are 0 to 10 minutes over here, and then 10, 20, 30, 40, 50. So if you choose your mid-latitude of 25 and draw a mark or make a note in some way. So this is our 25 mid-latitude. This now represents 1 degree of longitude. So from the 50 mark all the way to the 0 mark, and then the additional 10 minutes is 60 minutes. And so this is going to be equivalent. So that's another way to set up the longitude marks. So let's do that on this side. And then we can use our ruler or triangles to connect these dots and draw our longitude lines. So now we've got 146 degrees west there, not true. Okay, so now we've got a latitude and a longitude scale, and we've got the ability to plot things. So if we wanted to plot a latitude, we've got our degrees here, and then our minutes here, 10, 20, 30, 40, 50, and 60. For longitude, we've got our longitude degrees up at the top or the bottom, and we can use this longitude scale to measure portions of it. So for instance, if I needed to, say, make a mark at 25 degrees, 10 minutes north, well, that would be 25 degrees and 10 minutes north. If I needed a longitude of 145 degrees and 20 minutes west, what I would do is use my dividers to measure out from 0 to 20. So that represents 20 minutes of longitude, and then I can make a mark over here to represent the longitude line. So that would be 145 degrees and 20 minutes of longitude. A couple of notes, you can use this in a few different ways. So for example, if you wanted to set this mid-latitude at 25 degrees north, and then this one at 25 degrees 30 minutes north, you can in essence zoom in the universal plotting sheet that way. The only change you need to make is you need to change these 5, 10, 15, 20, and 25. So each of these, instead of representing 10, now represents 5. So you can kind of zoom in the maneuvering board that way. Longitude you need to account for as well. So instead of 60 minutes down here, it would be 30 minutes down here. And then another thing you can do, we'll recycle this one, is if you were operating in the southern hemisphere, let's say this was 25 degrees south. First of all, remember that latitude increases this way, so that would be 26 and this would be 24 degrees south. Longitude works the same way, so you could use this or your tools here to determine longitude lines. The only thing you need to do is change these 10, 20, 30, 40, 50, and then 60 to the 25 mark there. So they would be inverted on the universal plotting sheet for the southern hemisphere. So this is a really, really powerful tool that you can use to set up charts if you don't have a nautical chart in your area that's of an appropriate scale. And we can definitely plot celestial sight reductions on this among a variety of other tasks. The time has finally arrived to plot a celestial LOP onto a universal plotting sheet. So let's work through this problem and talk about the steps. The first is going to be to create the universal plotting sheet for the specific situation we are in. So if our assumed latitude is 25 degrees north, that's always a good place to put for your center latitude. This would be 26 degrees north. This would be 24 degrees north. There's a couple of techniques for plotting the longitude differentials. As we talked about, we can use this outer ring or we can use the scale down at the bottom. We'll go quick and dirty in this case and plot our longitude marks this way. So our assumed longitude is 144 degrees and 13 minutes. So let's just call this 144 degrees west. This would be 143 degrees west, and this would be 145 degrees west. So now we've got our universal plotting sheet set up, so we can kind of move forward into the plotting portion. So the first step, number one, is going to be to plot the assumed position. So the assumed position in this case was 25 degrees north and 144 degrees 13 minutes west. So we've got our latitude line here. It's generally going to be along the center latitude at all times. So we need to measure 13 minutes on our longitude scale down here. So since it's a center latitude of 25 degrees north, we don't necessarily have to draw the line since it's already there. But for illustration purposes, we'll do that. That's the one we're going to use. So I need 13 minutes. So here is 10 and here is 0. So I can go 10 minutes and then an additional 3. So 10, 1, 2, and 3 to get our 13 minutes. So that would put this mark right over here. And we can now draw our assumed position. So this is our AP, our assumed position. So this is what we determined in step 3 to solve a triangle in step 4, and now we've done some comparisons. And so in this case, maybe we determined that the azimuth was 210 degrees true, and the intercept, when comparing HC to HO, was 10.5 minutes away. So the computed was greater, so we were away in this case. So step number 1, or I guess step number 2, is going to be to plot the azimuth, and that's 210 degrees true. So the center represents the center mark, the outer perimeter is the circle, and then the numbers on the inside give you the true bearings around there. So 210 degrees would be something like this. So if we run that over to the AP, we can kind of plot in both directions, but towards 210 is towards the GP. So I like to just plot the GP to make sure I know what orientation things are. So if this is the AP, the assumed position, this is the direction towards the GP. It's probably thousands of miles away. But ultimately what we're going to do now is plot either towards or away from the GP in this case. So our intercept was 10.5 minutes. So we need to measure 10.5 on the latitude scale. This is the only place you can measure distance, and then make a mark away from the GP. So there's our mark. So this right here represents our intercept. So we plotted our assumed position, then we plotted the azimuth in both directions, and then we compared the computed height to the observed height. And if we were towards it, we would have plotted in this direction, some intercept over here. But in this case, we're away from it, so we plot our intercept away. And the piste de resistance here is a perpendicular line, represents the line of position. And you would label it maybe from the sun at 10, 12, 46, or whatever time we observed it in this case. So very important to note what's going on here. There's a lot of lines and a lot of things happening. But this right here, this LOP, is the key point. So you could, if you were doing this in pencil, you could erase some of the other stuff and just leave the LOP. This LOP technically represents a tangent. It represents a tangent to the circle of equal altitude that extends out in all directions all the way around the Earth. Usually it's like thousands of miles wide. So this line being a tangent to that circle is totally fine. It's practically going to be the same thing on a scale of kind of the Earth. So in reality, this circle of equal altitude extends out in all these kind of directions, goes all the way around the Earth and back. This is the direction towards the GP. So the GP of the sun is some thousands of miles away this way, and you've got your LOP, your line of position. So if you had, a lighthouse out here or something, and you could get a range from it or a bearing from it, you can kind of cross these bearings to get a fix. Or if you had two celestial objects, if you had another AP, and another kind of bearing and a LOP, then you can get your fix that way. So one celestial object, one LOP, but it is an amazing accomplishment at this point in the course. So work through these problems of plotting LOPs, and it's going to be very helpful later when we do multiple objects or running fixes. This video will discuss the basics of running fixes. This is a technique that you can use when you don't have two simultaneous bearings to cross. Instead, you're going to use one and then advance it into the future to use it again a second time. So in this case, we've got two bearings from Bartlett Reef Light, which is right here on this little chartlet, and our course is 270 and our speed is 4 knots. So we're like a slower boat kind of thing. So really the first step is just plot the LOP from Bartlett Reef Light at 340 for 12 o'clock. So I'll use this tool. You can use triangles or anything like that you like. I'll set this to 340, roll it to Bartlett Reef Light, and lay down an LOP. Always a good idea to label these too, so I'll label this as Bartlett Reef Light at 1200. So that's a normal process for a line of position, no big deal. Where the running fix comes in is we're in essence going to take this and we're going to move it into the future. So later on at 1300 we have another line of position, but for demonstration purposes I'm going to advance this one first. And so what we need to know is from 12 to 1300, how far did we move to the west? Our course was 270, our speed was 4 knots. Well, it's going to be 4 miles. So you don't have to do this this part, pen and paper on the chart. You can do it kind of mentally, but if you set up your ruler or your tool to your course and then pick like any point on this line, you may be tempted to pick one of the ends of it, but just to demonstrate, I'll pick any point. And just imagine you're going to advance it off into the future, 270. How far will you do that? Well, it'll be 4 miles. So we'll set this to 4 miles, make a little mark. And that's how far this LOP is going to advance in 1 hour, 4 miles. So really all you need to do then is take the existing LOP and parallel it to the little mark that you made. And this right here represents the LOP from 1200 to 1300. I drew it super huge because you need to know it doesn't have to be exactly the same as what you drew previously. It just represents a line that you advanced 4 miles at 270 degrees true. So this is subject to, error because maybe there was some current or maybe your instruments were not correct, but it's the best thing that you have for this secondary fix. Now, at 1300, you can lay in the 050 to Bartlett Reef Light. Label that one as well. So that's 1300 Bartlett Reef Light. And now you've got your running fix. All right, so key points here are plot your original line of position just like you normally would. And then in this case, we illustrated kind of the advancing of it first, but you don't have to do it first. Maybe plot your second LOP at 1300. And to advance it, the key point is to go in the direction that you were sailing at the distance that you would cover in the interval between them. And really just take that LOP and move it down the line. It doesn't have to be perfect replica. You don't have to draw this stuff if you don't want. That's just for illustration purposes. But if you advance that LOP where they cross is your running fix. It's not as good as a fix, but it's better than nothing else. So yeah, running fix is a great tool, and the fundamentals are helpful to get down before you kind of dive into the celestial version of the running fix. Now that we know a little bit about lines of position and running fixes, in the next two videos we're going to plot celestial LOPs and celestial running fixes to give us a good indication of how we can plot fixes on a chart and actually use this information that we've worked so hard for. Let's work this running fix problem. Given two lines of position based on a celestial site, we'll do a running fix to get our position at approximately noon. So the first site is at 0938. We observe the sun. The AP for the site is 28 south, 5208 west. It gives an azimuth and an intercept. So first thing we need to do is set up the plotting sheet. So given that we're going to be in the vicinity of 28 degrees south, it probably makes sense to put that as our middle latitude. So that would make this 27 degrees south and this 29 degrees south. We can also invert these marks here just to keep ourselves straight in the southern hemisphere. Lastly, down here we'll make a mark at 28 for our mid-latitude, just to remind ourselves about the longitudes. Speaking of longitudes, the AP for the first site is 5208 west. The AP for the second site is a latitude line, so we don't have a longitude. So we might as well set this to like 52 west for the center longitude, and then we can use our ruler or triangles or whatever method you prefer, these longitude marks here. So this would be 51 west and 53 west. So next up, we'll plot the AP for the first site. So that's 28 south and 5208 west. So I'll measure out 8 minutes down here. And that's going to be our assumed position for the first site. So I often label them AP1 just to keep it clear. So the azimuth for this site was 082.8 degrees true. So we'll spin that out here. 083 basically. And we'll run it in both directions from the AP just to keep things clear. So this is the direction towards the GP of the sun in this case. The intercept is 2.1 miles away, 2.1 minutes away. So I can measure 2.1. It's pretty small in this case. And so we're going to go away from the GP. And then we make our LOP perpendicular to this. And we can label it appropriately. So LOP, line of position from the sun, and the time was 0938:47. So that's pretty straightforward so far. The next step is going to be to plot our next line of position. So that next line of position happened to be a noon site for latitude, which was 27 degrees 42.1 south. So we can just set this up. Here's 27 south. Here's 28 south, here's 2740. So we're going to be at 42.1. So we'll just call that our latitude line. So this is maybe a noon site of the sun. It wasn't exactly noon, but it was local noon. So it was 11:58:42. You can choose how you want to label these things, but keeping things clear, I think, is a good way to do it. So our next challenge is going to be to take this morning LOP and advance it in the direction of travel of the ship. So the ship was heading kind of towards the northeast at a certain speed. So we need to advance this LOP and cross it with our noon sight to get our running fix. So the first step in that process is going to be to determine kind of like how far to advance that. And the way that we're going to do it is we're going to need to figure out how much time has elapsed. So the second sight was at 11:58:42. And the first sight was at 09:38:47. So how much time has elapsed between those two? Well, if I'm doing mental math or mental math with a calculator, I might take this 58 and make it 57, and take this 42 and make it 1:02, because we've got 60 seconds in a minute. So then 1:02 minus 47 is 55. 57 minus 38 is 19. Oops. And then 2 hours there. So 2 hours, 19 minutes, 55 seconds. We need to turn that into kind of decimal notation. So a couple of ways to do that, but my preferred way is to say, all right, 55 out of 60 is how much? So we got 2 hours and 19.92 minutes. And then this 19.92 is how much of an hour? So 19.92 divided by 60 is 0.33. So we've got 2.33 hours. That's merely one way of determining this time difference, but that's my preferred way. So then our travel is going to be at 19 knots. So how far will we go in 2.33 hours at 19 knots? 2.33 times 19 gives us 44.3 miles. Now, the direction of travel was 036 degrees. So many ways to advance this LOP, but in essence, we need to move this in the direction of 036, so up and to the right, for a distance of 44.3 miles. So my preferred way is to kind of set a, our mark here for 036 degrees. Oops. 036 degrees true. And then I pick a point on the first LOP and I just kind of advance it up a little bit. So if this was pencil, that could be a line that I erase later, or perhaps I draw it in dotted marks or something. And then we need to go 44.3 miles. So remember to go kind of upside down here because it's the southern hemisphere. So 44.3, that's good. So that is where we need to advance this LOP to. So we take it from here, we advance it to there. So I'll set up my rolling ruler. I've got it set to the first LOP, just rolling it over to the second LOP. And there we go. So these two lines are parallel here. So I might label this, LOP 093847 to 115842 to let me know that I've advanced that LOP. So now this one and this one occur at the same time. So this is our running fix position at 115842. Again, for real plotting, you could round this to the nearest minute, but in essence, that is our running fixed position. So that is sometimes known as sun, run, sun. So you take a sun site, you run for a while, and then you take another sun site, and you cross them for a running fix. The key, if you're doing this in real life, is, in essence, the sun rises in the east and it sets in the west. So if you're in the southern hemisphere, the sun appears to travel like this, and it's usually to the north of you, unless you're like in the tropics. So it usually goes that way. So in the morning, if the sun is over here, you're going to end up with an LOP that's kind of oriented like this or something like this. So this one extends all the way around the world, around the GP of the sun and back. As the sun gets closer and closer to your meridian, that angle is going to change until it eventually becomes the noon sight for latitude, which is just a latitude mark. In the afternoon, it will continue to change again as the sun is over here till you get something like this. So as long as you allow a couple of hours to pass, you're going to get two lines that cross really well. If you were to shoot one, at 9 a.m. and the other one at 9:15 a.m., there's not going to be enough difference for these to kind of cross. So usually a couple of hours for these solar running fixes. But in essence, that is a solar running fix. The core of what you'll do out there when you're doing celestial navigation during the day using the sun. An LOP in the morning, a noon sight for latitude, an LOP in the afternoon, and then stars in the evening, and that's kind of a full day of navigation. The three-body fix is a very satisfying thing that you can do, especially during star time. Sometimes during the day you can get the sun and the moon, occasionally the sun, moon, and Venus. But around star time, in morning and evening twilight, you can very easily get three or more objects to plot at pretty much the same time, which gives you almost an instantaneous fix. So a couple of key notes. We're going to assume that all of the stars that we shot in this case were observed at the same time. If it's within roughly a couple of minutes, it's totally fine to plot that on a universal plotting sheet to give you a fix for a certain time period. If you're moving very quick, or if you're very slow with your sights going from body to body, then you may need to advance some of the LOPs in a running fix. But in essence, you would take a quick round of celestial sights, you would then go reduce them, and then kind of now plot them all here. So we've got three sights, we've got assumed positions for each, azimuths for each, and intercepts for each, and we want to plot a fix in this case. So for the first one, the AP is 30 degrees north and 130.14 west. So I've already set up the universal plotting sheet. You probably feel okay with that by now, but if you want more practice, definitely go check that out. So for the longitude, 130.14 west, I'll just measure out 14 minutes down here using the tool, and I'm going to plot assumed position 1. And this is where it is important to label things. So if you had the star name, you could call it assumed position Acrux or assumed position, Doobie or something, but we're just going to call it AP1 in this case. So its azimuth was 110 degrees true. So we'll set our ruler. You could use triangles or another tool to 110, roll it to the AP, and then plot in both directions. Try not to clutter up the page too much if you do have a lot of plots coming your way. So we'll label this as GP for kind of training purposes. And then the intercept was 3 miles away. It's a pretty small intercept, which is good. So that's our intercept, and we can plot a perpendicular line to that to get our LOP. So this is LOP number 1. All right, so if you were working in pencil, this is a time that you could probably erase the azimuth line and just leave the LOP. That's an option for you. For the second one, our latitude was 30 degrees north, 130.36 west. So again, we'll use the tool down here to measure out 36. So 2, 4, 6, and then spin it to 30. So now I've got 36 minutes set. And we'll make a mark for AP2. This azimuth was 251, and it was towards. So we'll spin over to 251, roll to the AP, and then plot towards. So I'll label this GP just to keep our orientation here. And the intercept was 6.5 minutes towards. So we'll set 6.5, measure towards, and then drop our perpendicular mark to represent the LOP. This is LOP2. Looks like I didn't draw LOP1 far enough for the dramatic reveal, so we'll do that. So now we've got a good fix by all means. Typically you want 3 objects, but 2 is totally okay to give you some good data. So for the third one, our AP was 29 degrees north. So remember, we're going to use a different latitude mark in this case. And that sometimes happens when you're trying to set up an LHA. Occasionally, it's not always the same latitude mark. The longitude was 130.17. So 2, 4, 6, 7, and 10 is 17. So that's AP3. And its azimuth was 001. So this is a star that is due north of you. So it could be Polaris in some cases, although there's a different way of plotting and reducing Polaris. You wouldn't typically use an assumed position and a GP and stuff. So, but there are stars that pass due north of you. And it's passing to the north of you. It could be, you know, passing at its upper transit, or based on your latitude, it could be what's known as lower transit as well, but it's due north of you in some way. So 001 is our azimuth. So we'll draw that up. And our intercept in this case is 28.0 towards. So we'll measure out 28 minutes. And we can make our mark there. You can already feel the anticipation of a perfect fix, right? So we'll make our LOP. So this is LOP3. And this would be our fix right there. So whatever time we shot this at, that would kind of be our fix. Zooming in just a little bit, these crossed pretty much perfectly, so you know that's your position. If you do get a different shape, like if you were to get 3 that cross kind of like this is what's known as a cocked hat, based on kind of the old school sailor hats, you know, you can imagine their head and stuff. And that's totally okay. Generally, you can pick a couple of different spots for where you want to put your fix if you end up with a cocked hat. Now, if it ends up being like huge, then you might need to redo your fix. But in essence, you've got 3 choices here of the 3 stars. So you might want to say, which one did I feel most confident in? Okay, maybe this one and this one. So in that case, rather than the center of the cocked hat, you may choose to offset it a little bit towards that direction. So it really depends on how big, you know, these cocked hats end up. This fix I would call just plot right in the middle of it, especially at this scale of a universal plotting sheet. But if you end up with a triangle, you can either plot in the middle to set up the difference being equal for each one, or if you felt more confident in a certain site, you can err on the side of that and put it in a different position. So your choice. That's a little bit of the art of celestial navigation as well. But what a great feeling to take 3 objects and reduce them down and then plot them into an excellent fix like this.